In class we looked at the limit of sine x over x as x goes to 0, and I've got it here on the screen. It's called the sinc function sometimes. It's this pretty little graph, and as we get closer and closer to 0 with x, you can see that y gets closer and closer to 1, and we actually proved that the limit was 1 in class. I want to go back and revisit that. We talked about it in terms of sine x and x sort of racing to 0. Sine x, sine of 0 is 0, and at 0 x is 0, so they're racing to 0, and somehow it's a tie. That's a very odd thing. So let me look at these two functions separately. Here's the two graphs side by side, sine x in blue and x in red, and you can see something really interesting going on here. I'm going to zoom in. Can you see the difference between the two functions at 0? The graphs are so close that they're virtually identical. That's why the race is a tie. That's why when they both go to 0 at the same time, you're dividing one number by the same number for all practical purposes. This is a fact that we can use to help our understanding and help us do limits more easily. In essence, what it looks like is near 0, the graph of the function sine x looks just like the graph of x. And if this graph were scaled to scale, we'd see that the slope of this line was 1, because that's the slope of x. So near 0, the graph of sine x looks just like x. And then, of course, if we put x over x, obviously we get 1. The next function we want to look at is cosine x minus 1 all over x. And I've got its graph up here. And it looks like, we're interested in the limit as x goes to 0, it looks like the limit should be 0. As we get closer and closer to 0, the y values get smaller and smaller from both directions. And actually, Google's smart enough to tell us that at x equals 0, it's actually undefined. You can see it there. So what happens if we take the same sort of approach and try to look at these as two separate functions racing towards 0 and graph them separately? Now in this case, you can see that they don't overlap, that the graph of cosine x minus 1 does not really look like the graph of x at all. And in fact, what happens to cosine x minus 1 is that it kind of flattens out. See this? It becomes flatter and flatter. If I zoom in further and further to cosine x minus 1, it looks like it's the function identically equal to 0. You see right in there? It's basically a flat, constant line that's got 0 height. Now if cosine minus 1 is 0, then cosine must look like the function 1, right? We can check that. So here's just plain old cosine. Let's look near 0. I'm going to zoom in really close. And you can see that the further we zoom in, the more it looks like cosine looks just like the constant function 1, right? Looks like a constant 1. You see that? If we zoom in really close. So if we think about the race, then the answer should become clear. In the top, in the numerator of this fraction, we've got something that looks just like 1. That's cosine x near 0. Looks just like 1. We've got 1 minus 1 is 0. And x, when it's close to 0 but not equal to 0, is going to cause this fraction to be 0 over some number, which is always 0. So we would expect it to be very close to 0, near 0. If we summarize this, then near x equals 0, sine x looks a whole lot like just plain old x, and cosine x looks a whole lot like just the constant function 1. And with that understanding, we can calculate other limits very easily. So let's take a look at 3 homework problems on page 45, 52, 53, and 54. These are all limits involving trig functions, and all of them have x going to 0. I've converted thetas to x's because it's easier to type on here. So I want to take these in parallel, do them all at the same time, and we're going to use the same trick on each one. So for the first one, we've got cosine x minus 1, but near 0 we know cosine is like 1. And at the bottom we know that near 0 sine x is like x. So this is like 1 minus 1 over x, which we've seen before. That should be a 0. The next one has sine 3x on the top. Well, if sine x is like x near 0, then sine 3x ought to be like 3x near 0. The bottom is just a polynomial, and I can factor an x out, and you notice that I can cancel an x on the top and the bottom. And if I cancel those and plug in x equals 0, because it's a rational function, if it's defined, then I should have the limit. In the top I got 3, in the bottom the x is going to become 0, so that 5 will go away, and I'll have just 3 over negative 4, so we'd expect the answer to be negative 3/4. And in the last case, we've got sine 3x, sine 5x. Those are going to become 3x and 5x near 0, and the bottom is already a polynomial, so let's rewrite that. And the 3x and the 5x multiplied together are 15x squared. I've gone ahead and done that simplification, but it's just 3x times 5x, which we're justifying because near 0, sine of stuff looks like stuff. Sine x looks like x, sine 3x looks like 3x. In the bottom, we've got another x squared. Those are going to cancel, and we should expect to get just 15. Now let's take a look at the graphs and see if the graphs confirm our expectations. So we said cosine x minus 1 over sine x looks like 1 minus 1 over x, which we should expect to get 0 near 0. And in fact we do. We get a limit of 0 according to the graph. For the second one, we had sine 3x over this polynomial. So here I've typed in the function, and it looks kind of like a sad face. If we look near x equals 0, you can see y is negative 0.7499. We're getting very close to negative 3/4, which confirms our suspicion empirically. For the last one, we had sine 3x times sine 5x over x squared, and we expected to get 15. Let's see what we get. You can see this graph looks kind of like the sinc function we know and love, and up at the top it looks like it peaks about right at 15. So this general method of approximating a function with its straight line approximation where we're taking the limit seems to work very well, and we'll come back to that later and show that this actually works for all kinds of situations.